Molybdenum. Molybdenum is a chemical element with symbol Mo and atomic number 42. The name is from Neo-Latin molybdaenum, from Ancient Greek mu lambda upsilon beta delta omicron molybdos, meaning lead, since its ores were confused with lead ores. Molybdenum minerals have been known throughout history, but the element was discovered in 1778 by Carl Wilhelm Scheele. The metal was first isolated in 1781 by Peter Jacob Hjelm. Molybdenum does not occur naturally as a free metal on Earth, it is found only in various oxidation states in minerals. The free element, a silvery metal with a gray cast, has the sixth highest melting point of any element. It readily forms hard, stable carbides in alloys, and for this reason most of world production of the element is used in steel alloys, including high-strength alloys and superalloys. Most molybdenum compounds have low solubility in water, but when molybdenum-bearing minerals contact oxygen and water, the resulting molybdate ion Mu24 is quite soluble. Industrially, molybdenum compounds are used in high-pressure and high-temperature applications as pigments and catalysts. Molybdenum-bearing enzymes are by far the most common bacterial catalysts for breaking the chemical bond in atmospheric molecular nitrogen in the process of biological nitrogen fixation. At least 50 molybdenum enzymes are now known in bacteria, plants, and animals, although only bacterial and cyanobacterial enzymes are involved in nitrogen fixation. These nitrogenases contain molybdenum in a form different from other molybdenum enzymes, which all contain fully oxidized molybdenum in a molybdenum cofactor. These various molybdenum cofactor enzymes are vital to the organisms, and molybdenum is an essential element for life in all higher eukaryote organisms, though not in all bacteria. In its pure form, molybdenum is a silvery gray metal with a Mohs hardness of 5.5, and a standard atomic weight of 95.95 g/mol. It has a melting point of 2623 degrees C. Of the naturally occurring elements, only tantalum, osmium, rhenium, tungsten, and carbon have higher melting points. It has one of the lowest coefficients of thermal expansion among commercially used metals. The tensile strength of molybdenum wires increases about 3 times, from about 10 to 30 GPa, when their diameter decreases from 5100 nm to 10 nm. Molybdenum is a transition metal with an electronegativity of 2.16 on the Pauling scale. It does not visibly react with oxygen or water at room temperature. Weak oxidation of molybdenum starts at 300 degrees C, bulk oxidation occurs at temperatures above 600 degrees C, resulting in molybdenum trioxide. Like many heavier transition metals, molybdenum shows little inclination to form a cation in aqueous solution, although the Mo3+ cation is known under carefully controlled conditions. There are 35 known isotopes of molybdenum, ranging in atomic mass from 83 to 117, as well as 4 metastable nuclear isomers. 7 isotopes occur naturally, with atomic masses of 92, 94, 95, 96, 97, 98, and 100. Of these naturally occurring isotopes, only molybdenum 100 is unstable. Molybdenum 98 is the most abundant isotope, comprising 24.14% of all molybdenum. Molybdenum 100 has a half-life of about 1019 Y and undergoes double beta decay into ruthenium 100. Molybdenum isotopes with mass numbers from 111 to 117 all have half-lives of approximately 150 ns. All unstable isotopes of molybdenum decay into isotopes of niobium, technetium, and ruthenium. As also noted below, the most common isotopic molybdenum application involves molybdenum 99, which is a fission product. It is a parent radioisotope to the short-lived gamma-emitting daughter radioisotope technetium-99m, a nuclear isomer used in various imaging applications in medicine. In 2008, the Delft University of Technology applied for a patent on the molybdenum 98-based production of molybdenum 99. Molybdenum forms chemical compounds in oxidation states from 2 to +6. Higher oxidation states are more relevant to its terrestrial occurrence and its biological roles. Mid-level oxidation states are often associated with metal clusters, and very low oxidation states are typically associated with organomolybdenum compounds. Mo and W chemistry shows strong similarities. The relative rarity of molybdenum, for example, contrasts with the pervasiveness of the chromium compounds. The highest oxidation state is seen in molybdenum oxide, whereas the normal sulfur compound is molybdenum disulphide MOS2. From the perspective of commerce, the most important compounds are molybdenum disulphide and molybdenum trioxide. The black disulphide is the main mineral. It is roasted in air to give the trioxide. The trioxide, which is volatile at high temperatures, is the precursor to virtually all other MO compounds as well as alloys. Molybdenum has several oxidation states, the most stable being +4 and +6. Molybdenum oxide is soluble in strong alkaline water, forming molybdates. Molybdates are weaker oxidants than chromates. They tend to form structurally complex oxyanions by condensation at lower pH values, such as 6 and 4. Polymolybdates can incorporate other ions, forming polyoxymetallates. The dark blue phosphorus containing heteropolymolybdate P3 is used for the spectroscopic detection of phosphorus. The broad range of oxidation states of molybdenum is reflected in various molybdenum chlorides. Molybdenum chloride MoCl6 is not known, although the molybdenum hexafluoride is well characterized. Like chromium and some other transition metals, molybdenum forms quadruple bonds, such as in MO2 and 4, which also has a quadruple bond. The oxidation state 0 is possible with carbon monoxide as ligand, such as in molybdenum hexacarbonyl, MO6. Molybdenite, the principal ore from which molybdenum is now extracted, was previously known as molybdena. Molybdena was confused with and often utilized as though it were graphite. Like graphite, molybdenite can be used to blacken a surface or as a solid lubricant. Even when molybdena was distinguishable from graphite, it was still confused with the common lead or PBS. The name comes from Ancient Greek mu lambda upsilon beta delta omicron molybdos, meaning lead. Although molybdenum was deliberately alloyed with steel in one 14th century Japanese sword, that art was never employed widely and was later lost. In the West in 1754, Bengt Andersson-Quist examined a sample of molybdenite and determined that it did not contain lead and thus was not galena. By 1778 Swedish chemist Carl Wilhelm Scheele stated firmly that molybdena was neither galena nor graphite. Instead, Scheele correctly proposed that molybdena was an ore of a distinct new element, named molybdenum for the mineral in which it resided, and from which it might be isolated. Peter Jacob Hjelm successfully isolated molybdenum using carbon and linseed oil in 1781. For the next century, molybdenum had no industrial use. It was relatively scarce, the pure metal was difficult to extract, and the necessary techniques of metallurgy were immature. Early molybdenum steel alloys showed great promise of increased hardness, but efforts to manufacture the alloys on a large scale were hampered with inconsistent results, a tendency toward brittleness, and recrystallization. In 1906, William D. Coolidge filed a patent for rendering molybdenum ductile, leading to applications as a heating element for high-temperature furnaces and as a support for tungsten filament light bulbs. Oxide formation and degradation require that molybdenum be physically sealed or held in an inert gas. In 1913, Frank E. Elmore developed a froth flotation process to recover molybdenite from ores. Flotation remains the primary isolation process. During World War I, demand for molybdenum spiked. It was used both in armor plating and as a substitute for tungsten in high-speed steels. Some British tanks were protected by 75 mm manganese steel plating, but this proved to be ineffective. The manganese steel plates were replaced with much lighter 25 mm molybdenum steel plates, allowing for higher speed, greater maneuverability, and better protection. The Germans also used molybdenum-doped steel for heavy artillery, like in the super-heavy howitzer Big Bertha, because traditional steel melts at the temperatures produced by the propellant of the 1-ton shell. After the war, demand plummeted until metallurgical advances allowed extensive development of peacetime applications. In World War II, molybdenum again saw strategic importance as a substitute for tungsten in steel alloys. Molybdenum is the 54th most abundant element in the Earth's crust and the 25th most abundant element in its oceans, with an average of 10 parts per billion. It is the 42nd most abundant element in the universe. The Russian Luna 24 mission discovered a molybdenum-bearing grain in a pyroxene fragment taken from Mare Crisium on the Moon. The comparative rarity of molybdenum in the Earth's crust is offset by its concentration in a number of water-insoluble ores, often combined with sulfur in the same way as copper, with which it is often found. Though molybdenum is found in such minerals as wulfenite and powellite, the main commercial source is molybdenite. Molybdenum is mined as a principal ore and is also recovered as a byproduct of copper and tungsten mining. The world's production of molybdenum was 250,000 tons in 2011, the largest producers being China, the United States, Chile, Peru, and Mexico. The total reserves are estimated at 10 million tons, and are mostly concentrated in China, the US and Chile. By continent, 93% of world molybdenum production is about evenly shared between North America, South America, and China. Europe and the rest of Asia produce the remainder. In molybdenite processing, the ore is first roasted in air at a temperature of 700 degrees C. The process gives gaseous sulfur dioxide and the molybdenum oxide. The oxidized ore is then usually extracted with aqueous ammonia to give ammonium molybdate. Copper, an impurity in molybdenite, is less soluble in ammonia. To completely remove it from the solution, it is precipitated with hydrogen sulfide. Ammonium molybdate converts to ammonium dimolybdate, which is isolated as a solid. Heating this solid gives molybdenum trioxide. Crude trioxide can be further purified by sublimation at 1100 degrees C. Metallic molybdenum is produced by reduction of the oxide with hydrogen. The molybdenum for steel production is reduced by the aluminothermic reaction with addition of iron to produce ferromolybdenum. A common form of ferromolybdenum contains 60% molybdenum. Molybdenum had a value of approximately $30,000 per ton as of August 2009. It maintained a price at or near $10,000 per ton from 1997 through 2003, and reached a peak of $103,000 per ton in June 2005. In 2008, the London Metal Exchange announced that molybdenum would be traded as a commodity. Historically, the Molybdenum Mine in southern Norway, opened in 1885, was the first dedicated molybdenum mine. It was closed in 1973 but was reopened in 2007. And now produces 100,000 kilograms of molybdenum disulphide per year. Large mines in Colorado and in British Columbia yield molybdenite as their primary product, while many porphyry copper deposits such as the Bingham Canyon Mine in Utah and the Chuquicamata Mine in northern Chile produce molybdenum as a byproduct of copper mining. About 86% of molybdenum produced is used in metallurgy, with the rest used in chemical applications. The estimated global use is structural steel 35%, stainless steel 25%, chemicals 14%, tool and high-speed steels 9%, cast iron 6%, molybdenum elemental metal 6%, and superalloys 5%. Molybdenum can withstand extreme temperatures without significantly expanding or softening, making it useful in environments of intense heat, including military armor, aircraft parts, electrical contacts, industrial motors, and filaments. Most high-strength steel alloys contain 0.25% to 8% molybdenum. Even in these small portions, more than 43,000 tons of molybdenum are used each year in stainless steels, tool steels, cast irons, and high-temperature superalloys. Molybdenum is also valued in steel alloys for its high corrosion resistance and weldability. Molybdenum contributes corrosion resistance to Type 300 stainless steels and especially so in the so-called superaustenitic stainless steels. Molybdenum increases lattice strain, thus increasing the energy required to dissolve iron atoms from the surface. Molybdenum is also used to enhance the corrosion resistance of ferritic and martensitic stainless steels. Because of its lower density and more stable price, molybdenum is sometimes used in place of tungsten. An example is the M series of high-speed steels such as M2, M4, and M42 as substitution for the T steel series, which contain tungsten. Molybdenum can also be used as a flame-resistant coating for other metals. Although its melting point is 2623 degrees C, molybdenum rapidly oxidizes at temperatures above 760 degrees C, making it better suited for use in vacuum environments. TZM, Ti, Zr, and some C, is a corrosion-resisting molybdenum superalloy that resists molten fluoride salts at temperatures above 1300 degrees C. It has about twice the strength of pure MO, and is more ductile and more weldable, yet in tests it resisted corrosion of a standard eutectic salt and salt vapors used in molten salt reactors for 1100 hours with so little corrosion that it was difficult to measure. Other molybdenum-based alloys that do not contain iron have only limited applications. For example, because of its resistance to molten zinc, both pure molybdenum and molybdenum tungsten alloys are used for piping, stirrers, and pump impellers that come into contact with molten zinc. Molybdenum is an essential element in most organisms. In fact, a scarcity of molybdenum in the Earth's early oceans may have strongly influenced evolution of eukaryotic life. At least 50 molybdenum-containing enzymes have been identified, mostly in bacteria. Those enzymes include aldehyde oxidase, sulfite oxidase, and xanthine oxidase. With one exception, MO in proteins is bound by molybdopterin to give the molybdenum cofactor. In terms of function, molybdoenzymes catalyze the oxidation and sometimes reduction of certain small molecules in the process of regulating nitrogen, sulfur, and carbon. In some animals, and in humans, the oxidation of xanthine to uric acid, a process of purine catabolism, is catalyzed by xanthine oxidase, a molybdenum-containing enzyme. The activity of xanthine oxidase is directly proportional to the amount of molybdenum in the body. However, an extremely high concentration of molybdenum reverses the trend and can act as an inhibitor in both purine catabolism and other processes. Molybdenum concentration also affects protein synthesis, metabolism, and growth. MO is as a component in most nitrogenases. Among molybdoenzymes, nitrogenases are unique in lacking the molybdopterin. Nitrogenases catalyze the production of ammonia from atmospheric nitrogen. The biosynthesis of the Fe-MoCo active site is highly complex. Molybdate is transported in the body as Mu42. Molybdenum is an essential trace dietary element. 4 mammalian MO-dependent enzymes are known, all of them harboring a pterin-based molybdenum cofactor in their active site: sulfite oxidase, xanthine oxidoreductase, aldehyde oxidase, and mitochondrial amidosine reductase. People severely deficient in molybdenum have poorly functioning sulfite oxidase and are prone to toxic reactions to sulfites in foods. The human body contains about 0.07 mg of molybdenum per kilogram of body weight, with higher concentrations in the liver and kidneys and lower in the vertebrae. Molybdenum is also present within human tooth enamel and may help prevent its decay. Acute toxicity has not been seen in humans, and the toxicity depends strongly on the chemical state. Studies on rats show a median lethal dose as low as 180 mg/kg for some MO compounds. Although human toxicity data is unavailable, animal studies have shown that chronic ingestion of more than 10 mg/day of molybdenum can cause diarrhea, growth retardation, infertility, low birth weight, and gout. It can also affect the lungs, kidneys, and liver. Sodium tungstate is a competitive inhibitor of molybdenum. Dietary tungsten reduces the concentration of molybdenum in tissues. Low soil concentration of molybdenum in a geographical band from northern China to Iran results in a general dietary molybdenum deficiency, and is associated with increased rates of esophageal cancer. Compared to the United States, which has a greater supply of molybdenum in the soil, people living in those areas have about 16 times greater risk for esophageal squamous cell carcinoma. Molybdenum deficiency has also been reported as a consequence of non-molybdenum supplemented total parenteral nutrition for long periods of time. It results in high blood levels of sulfite and urate, in much the same way as molybdenum cofactor deficiency. However, the neurological consequences are not as marked as in cases of congenital cofactor deficiency. A congenital molybdenum cofactor deficiency disease, seen in infants, is an inability to synthesize molybdenum cofactor, the heterocyclic molecule discussed above that binds molybdenum at the active site in all known human enzymes that use molybdenum. The resulting deficiency results in high levels of sulfite and urate, and neurological damage. High levels of molybdenum can interfere with the body's uptake of copper, producing copper deficiency. Molybdenum prevents plasma proteins from binding to copper, and it also increases the amount of copper that is excreted in urine. Ruminants that consume high levels of molybdenum suffer from diarrhea, stunted growth, anemia, and achromatrichia. These symptoms can be alleviated by copper supplements, either dietary and injection. The effect of copper deficiency can be aggravated by excess sulfur. Copper reduction or deficiency can also be deliberately induced for therapeutic purposes by the compound ammonium tetrathiamolybdate, in which the bright red anion tetrathiamolybdate is the copper chelating agent. Tetrathiamolybdate was first used therapeutically in the treatment of copper toxicosis in animals. It was then introduced as a treatment in Wilson's disease, a hereditary copper metabolism disorder in humans. It acts both by competing with copper absorption in the bowel and by increasing excretion. It has also been found to have an inhibitory effect on angiogenesis, potentially by inhibiting the membrane translocation process that is dependent on copper ions. This is a promising avenue for investigation of treatments for cancer, age-related macular degeneration, and other diseases that involve a pathologic proliferation of blood vessels. In 2000, the then U.S. Institute of Medicine updated its estimated average requirements and recommended dietary allowances for molybdenum. If there is not sufficient information to establish EARs and RDAs, an estimate designated adequate intake is used instead. An AI of 2 micrograms of molybdenum per day was established for infants up to 6 months of age, and 3 μg/day from 7 to 12 months of age, both for males and females. For older children and adults, the following daily RDAs have been established for molybdenum: 17 μg from 1 to 3 years of age, 22 μg from 4 to 8 years, 34 μg from 9 to 13 years, 43 μg from 14 to 18 years, and 45 μg for persons 19 years old and older. All these RDAs are valid for both sexes. Pregnant or lactating females from 14 to 50 years of age have a higher daily RDA of 50 μg of molybdenum. As for safety, the NOM sets tolerable upper intake levels for vitamins and minerals when evidence is sufficient. In the case of molybdenum, the UL is 2000 μg/day. Collectively, the EARs, RDAs, ACE, and ULs are referred to as dietary reference intakes. The European Food Safety Authority refers to the collective set of information as dietary reference values, with population reference intake instead of RDA, and average requirement instead of EAR. AI and UL defined the same as in United States. For women and men ages 15 and older, the AI is set at 65 μg/day. Pregnant and lactating women have the same AI. For children aged 1-14 years, the ACE increase with age from 15 to 45 μg/day. The adult ACE are higher than the US RDAs, but on the other hand, the European Food Safety Authority reviewed the same safety question and set its UL at 600 μg/day, which is much lower than the US value. For US food and dietary supplement labeling purposes, the amount in a serving is expressed as a % of daily value. For molybdenum labeling purposes, 100% of the daily value was 75 μg, but as of May 27, 2016 it was revised to 45 μg. A table of the old and new adult daily values is provided at reference daily intake. The original deadline to be in compliance was July 28, 2018, but on September 29, 2017 the Food and Drug Administration released a proposed rule that extended the deadline to January 1, 2020 for large companies and January 1, 2021 for small companies. Average daily intake varies between 120 and 240 μg/day, which is higher than dietary recommendations. Pork, lamb, and beef liver each have approximately 1.5 parts per million of molybdenum. Other significant dietary sources include green beans, eggs, sunflower seeds, wheat flour, lentils, cucumbers, and cereal grain. Molybdenum dusts and fumes, generated by mining or metalworking, can be toxic, especially if ingested. Low levels of prolonged exposure can cause irritation to the eyes and skin. Direct inhalation or ingestion of molybdenum and its oxides should be avoided. OSHA regulations specify the maximum permissible molybdenum exposure in an 8-hour day as 5 mg/m3. Chronic exposure to 60 to 600 mg/m3 can cause symptoms including fatigue, headaches, and joint pains. At levels of 5000 mg/m3, molybdenum is immediately dangerous to life and health.